Okay, so here we go with the Chapter 4 homework review. The performance on this homework was pretty good overall. The average was just around a 10 out of 12, but there were a few things we had trouble with, and a couple of them were things that I just, for various reasons, glossed over in lecture, mainly due to time constraints. So I'll go over those in more detail right now, and hopefully that'll clear up some things for you. Alright, so the first question that I want to go over is about the shapes of molecules, and specifically what this one is asking is how many of the following molecules have all of their atoms in the same plane. Now to do this we have to consider the shapes of all the atoms, but there is a shortcut we can take for a lot of the answer choices. So this is not even a chemistry argument, this is a geometry argument. If you have three atoms, they have to be in the same plane. Okay, there's no way to arrange three things without them all being in the same plane. 3 points define a plane. So for any of these answer choices that only have three atoms total, they must be planar. So OF2 has to be planar, CO2 has to be planar, BeCl2 has to be planar. We talked in class if there's three atoms, you can have either a bent or a linear geometry. Those are the only possibilities. But either of those, all three atoms are in the same plane, so it doesn't really matter which one of those geometries these fall into. They have to be planar. Now for the rest of them, we have to draw their structures and consider the VSEPR treatment of these. So this first one here is a little bit of a difficult one because we have really two central atoms, two carbons bonded to each other. The Lewis structure is given to us pretty much. We don't even have to draw it out. And when we get this structure here, sorry, it's an H. Okay, we have this structure here where we have two carbons double bonded to each other terminated by hydrogens. If we look at each carbon atom, we consider the steric number of that, how many things are bonded to it. Each one has three things. It has two hydrogens and the other carbons. So each of these is going to be an AX3 center, which is going to make each of them trigonal planar. And same with this one. It's AX3, three things bonded to it, trigonal planar. No lone pairs in any of these, of course, for carbon. Alright, so we have two trigonal planar centers attached to each other, so that would suggest then that this is a planar molecule. We have two planes, and this carbon and these two hydrogens are in the same plane, and it has to be in the same plane as this other carbon too. So basically all four of these atoms, I'm going to put check marks next to, those are in the same plane because of the AX3 structure for this first carbon. For the second carbon, it's also planar, so that puts the other two hydrogens in that plane as well. So if we look at the model of this, again, when you're learning these types of things, building models is helpful. Here's what this looks like. This is a model of that molecule, and as you can see, it's a perfectly flat molecule. The hydrogens, these white balls on the outside, are in the same plane as the carbons, these black ones here. Okay, so we have a planar molecule. When you have two sp2 centers bonded to each other, they have to all be in the same plane. There's no other way to do that. You can't twist them relative to each other. And the other way to think about this too, which is probably even a little bit more rigorously true, is that why? So the question might be, well, why can't this plane, this second plane here, be twisted relative to the first plane? And that's because of the bonding. So remember that we have a pi bond in this molecule, we have a double bond. So what that means is that you have your hydrogens out here on the outside, and to form this pi bond we need to have a p orbital above and below the plane. So this is sort of taking it to another level, but it's also important to think about. And when we do this, in order to maintain that side-to-side overlap and form this pi bond here, you need to have the two molecules in the same plane. If you try to twist these two relative to each other, you're going to break the pi bond. So if we go back to our model for a second, okay, we have this here representing a double bond. We can't twist these without breaking the bond. The only way to twist these planes relative to each other is to break the pi bond, and then we can move them about, but that would break the double bond that we have in our structure. So the point is, one thing we didn't talk about with respect to pi bonds is that they don't have any rotational freedom. When you have a pi bond, the planes are fixed. You can't rotate a pi bond without breaking it. Okay, so that one was a little bit of a hard one to think about, but this one is in fact planar. And then finally, if we go to H2CO and NH3, okay, H2CO has this structure. We draw the whole thing out. Lone pairs on oxygen. So this is AX3, which we know is trigonal planar. And then NH3, sorry, we'll move this one over a little bit. We talked about this one in class also. This one is AX3E, which is going to be a trigonal pyramidal geometry. And so that is going to be non-planar. So in this case, the 3 hydrogen atoms do not sit in the same plane as the nitrogen. It's a pyramidal structure. So this one's not planar, but the rest of them are. So that's how we wanted to approach that problem. For some of them, you could take a shortcut, but for others, we had to think about the structure in more detail. Okay, so then 5 of these 6 have the same molecule, have their molecules. Sorry, 5 of these 6 molecules all have the atoms in the same plane. Now, the other aspect of molecular structure that I didn't have a ton of time to talk about is polarity. So I gave you sort of that chart at the end, which, at least for the simple AXE molecules, allows you to quickly predict polarity. But the rationale behind this is that if we have polar bonds, so if we have two atoms bonding to each other, A, B, we know from our discussions before that if their electronegativities are different, they're going to have some dipole that points towards a more electronegative atom. So if we suppose up here that B is more electronegative than A, we would have a dipole that points like this. Now, if you're going to have a molecule that has more than 2 atoms in it, whether it's polar or not depends on whether those dipoles cancel out or whether they add together to give a net dipole in some direction. And so that's what we want to think about here. So here we're talking about dichloroethylene, which has 3 different isomers, they're called, which are 3 different structures where the hydrogens and the chlorines are arranged in different orders and different positions relative to each other around the molecule. Now we want to know which of these is polar. So to do that, we have to think about the individual dipole moments. So looking at electronegativity values and from just periodic trends, we know that of these, hydrogen has the smallest electronegativity, it's about 2.1. Carbon is going to be 2.4 on the Pauling electronegativity scale, and chlorine is going to be, I believe, 3.0. So those are the approximate electronegativity values. Whether we realize it or not, the point is that none of these, we know these are all different atoms and none of them have the same electronegativity, so there's going to be dipoles in this molecule. So if we draw the individual bond dipoles, remember they point towards the more electronegative atom. Between carbon and chlorine, there's always going to be a dipole pointing towards chlorine, like this. And then between hydrogen and carbon, there's going to be a small dipole pointing towards carbon. Now, carbon-hydrogen bonds are effectively nonpolar. There's not a huge difference in electronegativity, but there is some effect. But however we want to look at this one, in this first molecule here, all of these dipoles sort of point down. They point down and in, so there's a net dipole pointing in this direction. Okay, so basically we're summing vectors here, and if all of these arrows, all these vectors add together, there's going to be a dipole pointing down. They don't cancel each other out. If we go to choice 2 here, we have dipoles pointing from hydrogen to carbon, but those two are pointing in exactly opposite directions, and then same with our carbon-chlorine dipoles, which point towards the chlorines. Those are in opposite directions. So here all of the dipoles cancel out, and so this one is going to be nonpolar, or it's going to have a 0 dipole moment. This first one I didn't write it here, but this one's going to be polar because the dipoles don't cancel out. And then finally this last one here, we draw dipoles from hydrogen to carbon and from carbon to chlorine. Again, we're pointing towards the more electronegative atom. And when we do this, this molecule is going to have a net dipole pointing to the right. All these arrows add up to give a dipole that points left to right as we've drawn it here. Okay, so this one's also going to be polar. So the question is, which of these has a dipole moment not equal to 0? That's going to be 1 and 3. So of these 3 possible structures, 2 of them are polar, and this middle one here, choice 2, is going to be nonpolar because the dipoles cancel each other out. They're oriented exactly 180 degrees relative to each other. Alright, so that's how we want to approach a problem with molecular polarity, and that's very much related then to this question here. Consider the molecules PF5, BRF3, BRF5, and SF4, which does not have a molecular dipole moment. So to do these ones, these are all AXN type structures, central atom and then atoms bonding to the outside. Fluorine is the most electronegative atom, so the dipoles are all going to point towards fluorine. And we want to figure out which ones of these do the dipole moments cancel out. So if we look at PF5, so that one is going to be an AX5 structure. So I'm skipping a lot of steps here. You should review how we draw Lewis structures and determine this, but PF5 has no lone pairs on the central atom, so it's going to be an AX5 structure, which is trigonal bipyramidal. And we said that all of the AXN structures with no lone pairs, so if it's AX2, AX3, AX4, AX5, AX6, all of those are nonpolar. So in this case, just like the ones before, all of the dipoles cancel each other out. These two, it's obvious. One points up, one points down. The ones on the trigonal plane of this molecule are a little less obvious because we have to talk about the dipoles in 2 dimensions now. But when you have a triangle of atoms like this and the dipoles all point towards the corners of the triangle, they also cancel each other out. So this one's nonpolar. BRF3, okay, so if we draw the Lewis structure for BRF3, it's going to have 28 electrons. It's going to have 2 lone pairs on the central atom. Okay, so this is going to be an AX3 E2 structure, which gives us a T shape. So these 2 central atoms on the lone pair. So we still have 5 total things bonded to our central atom. This is also a steric number of 5, but the 2 lone pairs now are arranged on the trigonal plane. So we have a T-shaped molecule. These 2 dipoles essentially cancel each other out, but we still have this dipole pointing right to left from bromine to fluorine. So this one's going to be polar. So it does have a dipole moment. BRF5. If we draw the structure for this, it's going to be, again skipping some steps, AX5E. Okay, so this is a AX5E geometry, which means we have a square pyramidal geometry. Now we have a lone pair here on the bottom. But if we draw the dipoles from bromine to fluorine, the ones that are on the square part of the molecule essentially cancel each other out. Alright, but then we have this net dipole pointing top to bottom, so this is going to be polar. Alright, and then finally if we have SF4, this one's going to be AX4E, so still a steric number of 5, but this is going to give us a seesaw geometry. Seesaw geometry. These dipoles pointing up and down essentially cancel each other out. I say essentially because these bond angles are distorted a little bit by the lone pair, but from a simple standpoint, these 2 cancel each other out, but then we have dipoles pointing from left to right and a net dipole that points in that direction, so this one's going to be polar as well. So of these 4 molecules, the only one that does not have a molecular dipole moment is going to be PF5. That's the answer choice we wanted to pick. So all the rest have 1 or more lone pairs. Now a shortcut we can take with these polarity questions, if it's again simple, AX and structures, central atom with some atoms bonded on the outside, if there's 1 lone pair, it's going to be polar. So if our central, when I say 1 lone pair, I mean on the central atom. Okay, so we don't really care about the lone pairs on the outer atoms. So if our central atom has 1 lone pair, then it's going to be polar. If the central atom has 2 lone pairs, then you have to think about the actual structure. So AX3E2 is polar, but AX4E2 would not be polar. I gave you that chart in the notes last week on Monday or Wednesday, I believe it was, and in that you're going to look at, those geometries are going to determine what the polarity is for the whole molecule. But if it's 1 lone pair, it's definitely going to be polar. You don't even have to think about it. And if there's no lone pairs, I guess that's another important one. If you have 0 lone pairs on the central atom, that's going to be nonpolar, if all of the x's are the same, as I said before. Okay, so these are some shortcuts you can take, but definitely learn how to rationalize these and think about these, these dipole moments for the individual bonds. Think of them as vectors that point towards the more or less negative atom, and think about whether they cancel each other out or whether they add up to give a net dipole in some direction. Alright, the next question I want to go over is on molecular orbital theory. So here we're comparing Be2 and H2, and we want to know something about the stability and the bond order and things of that sort. So we have to draw the molecular orbital diagrams. Now, beryllium is the electron configuration is 1s2, 2s2, fourth atom on the periodic table. So the valence electrons are s orbitals, so we only need to draw the molecular orbitals that derive from s orbitals. You don't need to draw the p orbital diagram for this one because there are no p valence electrons. So remember, when we draw that diagram, we have on the outside of our diagram we have the individual atoms. Beryllium, we only consider the valence electrons. So we're going to draw the mixing of the two s orbitals. Remember that s orbitals mix to give two different kinds of orbitals: a sigma, which is bonding, and a sigma star, which is anti-bonding. Alright, so beryllium, each of these has two 2s electrons, so we have a total of 4 electrons to go into our diagram. We fill from the bottom to the top. And so when we do that, we've filled our sigma and our sigma star 2s. So Be2 here is going to have a sigma 2s to sigma star 2s to valence configuration. So both the bonding and the anti-bonding orbitals are filled, which means that we would predict that this has a bond order of 0. Now, when something has a bond order of 0, that's another way of saying it's unstable. It doesn't exist. You have no net bond between the two beryllium atoms, so you would never observe Be2 in nature. Okay, it's just not a stable molecule because all of the whenever the bonding and anti-bonding orbitals are filled, you have no net bond between them. So this is an unstable molecule. So anything that claims that Be2 is more stable than H2 is probably wrong. We can verify for H2 now. We did this one in class, and we know already that it's a single bond. Valence bond or theory predicts that, and that's what molecular orbital theory gives us as well. So for H2, we have only one 1s electron in our valence shell. So if we make the sigma 1s and the sigma star 1s molecular orbitals, we fill them up with those 2 electrons. We get a sigma 1s2 configuration, which means we have a net bond order of 1. Okay, we have one filled bonding orbital, so there's a single bond. So because of this, we would expect H2 to be more stable than Be2. And when you're comparing stability of molecules, it's really just bond order that you want to think about. The number of unpaired electrons, which orbitals are filled, is really not important. It's just a matter of bond order. And if something has a 0 bond order, it's going to be unstable. So if we compare all these choices here, we want to figure out which ones of these is true. Be2 is more stable because it contains both bonding and anti-bonding valence electrons. Remember, we just got done saying Be2 is not stable because both of those orbitals are filled. So that's not a true statement. H2 has a higher bond order than Be2. That is correct. We saw that H2 has a bond order of 1, Be2 is 0. H2 is more stable because it only contains sigma 1s electrons. That would also be true because in H2, the sigma star 1s, this orbital here is unoccupied. So we have our antibonding orbital unoccupied, which gives it greater stability. And then finally, H2 is more stable because it is diamagnetic, whereas Be2 is paramagnetic. Now, H2 is diamagnetic. Remember, diamagnetic means all paired electrons, but Be2 is as well. Be2 does not have any unpaired electrons. So both of these molecules are diamagnetic. So that's another property we can say. So both are diamagnetic. Alright, so that's not a difference between them. And that really has nothing to do with the stability from our standpoint. So even if they did have different magnetic properties, you could not directly predict the stability from that. But they are both diamagnetic anyway, so this statement is false just on that premise. Okay, so from molecular orbital theory, we draw the diagrams. I gave you 3 different types of molecular orbital diagrams in class. This one that I'm showing you here is a simple one for s orbitals. And we saw that there's 2 different diagrams involving p orbitals depending on which part of the periodic table you're in, whether it's boron, carbon, nitrogen, or whether it's oxygen, fluorine, neon. So which column of the periodic table will determine which diagram is valid. And so when you're doing these types of problems, you draw the diagram, you fill in the correct number of electrons, and then you evaluate which orbitals are filled, what's the bond order, as I showed you how to do in class, and how many unpaired electrons there are. And those are the types of things we'll be answering questions about. Alright, finally the last one here is sort of a Lewis structure of a more complex organic molecule. So again, here instead of just having one central atom and some outer atoms. It's a more complicated structure, and we want to try to get the Lewis structure for this. Now, doing this the long way, the way that I showed you in class, where we add up valence electrons, put in single bonds, count all the electrons, that takes quite a while for this type of structure because there's so many atoms involved. So we want to look at some shortcut ways of doing this. So for these types of organic molecules, when we say organic molecules, we mean molecules that pretty much primarily contain carbon, hydrogen, nitrogen, oxygen. Maybe they'll have some halogen atoms in them as well, some fluorine or chlorine as well. But there's some shortcuts we could take. First of all, hydrogen of course forms one bond. We don't have any hydrogens in this structure, but if there were, you would just stop at a single bond, no lone pairs, no double bonds, of course, for hydrogen. And then for the rest of these atoms that are going to be common in these structures, there's some patterns we want to follow. They're all going to complete octets. So if you have carbon, nitrogen, oxygen, or X, which is a halogen, so these possibilities, all of these guys in these types of structures are going to have complete octets, exactly 8 electrons. You're not going to exceed the octet rule in any of these types of structures typically, because carbon, nitrogen, and oxygen cannot exceed their octet rule. And in organic molecules, the halogen, the X atoms, are going to be outer atoms, in which case they don't exceed their octet either. So we're not going to exceed the octet rule in any of these structures, so that's the first thing. And then the way we want to do this for these different atoms to avoid formal charges is as follows. So carbon is going to form 4 bonds with 0 lone pairs. Okay, so you're going to form 4 bonds to carbon and have no other non-bonding electrons. Nitrogen tends to form 3 bonds with 1 lone pair. These are for neutral organic molecules that we're primarily talking about here. Oxygen forms 2 bonds and has 2 lone pairs. And then the halogen atoms, fluorine, chlorine, bromine, they're going to form 1 bond and have 3 lone pairs. Okay, so when we're filling in Lewis structures like this, we have to keep these patterns in mind. That'll hopefully save us some time. And this is something you're going to want to get good at if you're going to take organic chemistry especially, is drawing these types of structures. Okay, so we go over to this skeleton here, which has single bonds drawn between carbon and nitrogen, but we're missing a bunch of bonds in here, maybe possibly some lone pairs as well. So probably the best place to start on these structures is on the outside, because the outer atoms are only bonded to one thing, and so the number of bonds they form and the number of lone pairs they have is going to be defined pretty easily. So for each of these nitrogens here, these are terminal atoms. That means they're on the outside, not bonded to anything else. And as I said over here, they want to form 3 bonds and have 1 lone pair. So we draw 2 more bonds to nitrogen in the lone pair. And all of these nitrogens are in the same boat. They have they're not bonded to anything else, so those 3 bonds should come in the form of a triple bond. So when I say 3 bonds, that means either a triple bond or 3 single bonds or 2 double bonds and single, some combination of 3 bonds in any case. But if they're only bonded to one thing, then it has to be a triple bond. Now if we then move into these carbon atoms here that they're bonded to, these carbons now have complete octets and 4 bonds. They have the triple bond, which is 3 bonds, and then another bond to the central carbon here. So these carbons here, 1, 2, 3, 4, already have 4 bonds. We don't want to add anything else to them. No lone pairs, no more bonds. Then finally we go to these central carbons here. As drawn, they have 3 bonds, 1, 2, 3. So to complete their octets and make them happy, we want to put a double bond in between them. That will make all of the carbons now have 4 bonds. We cannot draw a double bond to the outer atoms because, as I just said, these outer atoms already have their full 4 bonds. So the only way we can do this to complete the octets is to draw a double bond there. So that's how we want to approach these types of problems. Keep these patterns in mind that I've listed over here and try to make sure that every atom has exactly 8 electrons when it's all said and done, except for hydrogen, of course, which only has 2 electrons or 1 bond. So now we have to answer the question, how many non-bonded electron pairs are there? So pair means 2 electrons. So each nitrogen has 1 lone pair of electrons. I'm circling them now. So there's going to be 4 non-bonding electron pairs, or lone pairs as we more typically call them. Alright, so that takes me through what I was going to cover today. These were the problems where we had success rates of less than 55% or so. So around half of you had trouble with these. So hopefully that clarifies some things. And if you have any more questions, please ask me during the week, or on the Blackboard forum would be great as well. All right, I'll see you next time.